Okay, so let's get into the details about how the backpropagation work with a general, a multiple input, multiple output neural network. Yeah, so look at this diagram, and then so we are going to input X into the input layer right here. So we have X1, X2 up to XD, and then so when we fit this input X into this neural network, we are going to collect the value of y1, y2 up to ynh, and then this information will propagate to the output layer Z1 to ZC, and then now, so that means when we have a vector X, and then we will collect the output Z, vector Z at the output, and corresponding to each sample X, we will have the target value, yeah, T1 up to TC, and according to what we have done before, we know that we are going to find the difference between the target value at and Z, and finally we are able to collect the training error, that is the sum of the square error, or we would represent like this, that is the L2 norm of the vector T minus Z, and then these two expressions, they are equivalent. And now what we are going to do, that is based on the training error, we are going to minimize J by adjust the value of W in these two layers. The first one, that is we are going to do the adjustment, find the adjustment of the hidden to output weight. That means we are going to find WKJ, yeah, so corresponding to the connection weight in between hidden layer and output layer, we have WKJ, yeah. So our objective, that is to find this partial D partial WKJ, so that we can find this delta WKJ as the adjustment. And now we are going to look at the green part of this neural network, because now we are going to look at how the change of the output, how the change of J with respect to these connection weight. Take a look at this one. So if we are going to zoom into this particular load, we call this is the output ZK, and then so just extract the green part right here, and then I'm going to put it in this diagram, yeah. So that means we have the output y1, y2, ynh, as well as the 1, and then all of them fit into this hidden node K. This hidden node K, that is this guy, yeah. So y1 to ynh and 1, that is these guys right here, and this is the ZK. That means if you are going to move this ZK, for example, when you pick Z2, you will choose this particular load. When you choose ZC, that would be this particular load, yeah. So now I just focus on the hidden node K, and now we want to do one thing, that is now we are going to find the difference TK minus ZK, and then so that is because when we consider all the Z right here, that is this error, yeah. Okay, now as I mentioned that I want to find the change of this J, so that with respect to WKJ, that would be one of this connection weight. When J that is 1, we are talking about this WK1. When J that is 2, we are talking about this WK2, and so on. So that means when we change this value of W, one of them, and then this change will propagate to J. So that's why we have partial J, partial WKJ. According to the train rule, we have partial J, the change of J with respect to ZK right here, and then ZK with respect to lat K, so we have partial ZK, partial lat K, and then partial lat K with respect to any of this one. That means actually we are going to find the change one by one, yeah, all of them we will consider, but now we particularly interested in one of them. This is WKJ, that would be any one of them. Okay, so once we formulate the problem like this, that is we would like to find the rate of change of J with respect to WKJ, and then so now we are going to look at that one by one. Partial J, partial ZK, because this is just the because we do the partial derivative, that means we consider all these variables to be constant except zk. So if you're going to look at this, so if we are going to look at a particular zk, and then the only variable that would be this zk. So dj dzk, it will give you this term. Yeah, so this term is well defined. And then now we are going to look at partial zk, partial lat-k. Partial zk, partial lat-k, that would be this term. Zk lat-k, and then zk, that is function of lat-k. Yeah, so zk, that is f of lat-k. So this term can be written as partial f lat-k with respect to lat-k, and then because at the moment we do not know this iteration function, so we are going to choose this iteration function that is to be differentiable. So I'm just use f prime to represent this is partial f partial lat-k right here. And then now we are going to look at this lat-k. This lat-k, this is the expression of the linear combination of y and w. It means that is y1 times wk1 plus y2 times wk2, and so on. So this is the lat-k in summation form, and then we expand that, we will just find out that is what exactly I just mentioned, y1 times wk1, y2 times wk2, and so on. Yeah. Now when we talk about the last term, partial lat-k with respect to one of this wkj, for example, one of the wkj that is in the middle, all the rest would be constant. So this term, if we do derivative with respect to wkj, and then so we would just find out that this term, that is yj. And now we already find out that the change of j with respect to wkj, that can be broken down into these three terms, and then each three terms, they are well defined, and we can calculate their value. So d partial j partial wkj, that is a numerical value we can find out. Yeah. Okay. And now this is the overall form. Once you know the training samples, plug it into this equation. You know tk, you know zk. Yeah, present the value, present the sample into the neural network. You can find out what zk it is, and then substitute that into this equation, and you find this part. Once you define the learning weight, and then you know the delta wkj, so now you know the way how to update these w. In the previous slide, we find the adjustment for the w in this layer. Now we move forward so that we are going to find the adjustment for this w in between the input and hidden layer. That is, we are going to find delta wji. Yeah. So this delta wji depends on the change of w with respect to this wji. Note that this wji, it can be any w in between the input and hidden layer. Yeah. Okay. So we are going to do the same thing. Based on the training samples, we find the training error in this form, that is j. And then what we are going to do next, that is to find the change of j with respect to wj in this particular form. We are going to apply the train rule. Yeah. So j with respect to y right here. Okay. And then that is the first term. And y with respect to let right here, y with respect to let j right here, that is the second term. And then net with respect to w, that would be the third term right here. Okay, so now we are going to look into the details term by term. That means first we are going to find out change of j with respect to yj, and then this term, and then this term. Yeah. Okay. Now we are going to do the same thing. Take a look at this term. This is the first term we are going to find. That is the change of j with respect to yj right here. When you change the value of j, and then that means we are talking about the change of j with respect to y1, y2, up to all the hidden nodes right here. Yeah. So take a look at this one. When you change yj, and then this change will propagate through the green line, and then this yellow line, and then this green line to change j. So that means when you change the change of j, that is, it will propagate back to this yj through all this path. Okay, so if we are going to take a look at this one, parcel j, if we just look at this yellow line, if we just consider the change of j with respect to yj according to this path, and then so we can write as parcel j, parcel zk, that is this term, parcel zk with respect to yj. And then this is only the contribution given by this yellow link. As I mentioned before, this change, the contribution, is propagated through all this green line. So we have to consider all this contribution from all the link right here. So that's why that is k, that is from 1 to c. We consider all this contribution, that is this term. So according to what we have done before, this parcel j, parcel zk, that is given by this summation term right here. So the next term we are going to find, that is the parcel zk, parcel yj. Yeah. So that is the change of zk with respect to yj. Yeah. Okay. Now just recall that in each hidden node we have two elements. Yeah. The activation function f as well as this summation, which will produce the lead kit. So when we consider this term parcel zk, parcel yj, and then so we are going to consider everything in between to apply the train rule again. So parcel zk with respect to let right here, and then the let with respect to yj right here. So we are going to make things simple now. Yeah. So parcel zk with respect to let k as what we have done before. That is the df d let kit. Yeah. So this is about the derivative of this function. Yeah. Okay. And then the next one, parcel let k with respect to parcel yj. Just to recall that, when we consider this let kit, we will have a linear combination of y1 times the length of this line, and then plus y2 times the connection weight w at this line, and then let k, it could be something like this. Yeah. So I just show the connection weight right here, wk1, wk2, and then up to wk0, and then so now we are going to represent let k as the weighted sum of yj. Yeah. So now parcel zk, parcel yj, that would be the term that would be the term wkj right here. So with this information, we are able to find out this term, and then this is the first term, parcel j, parcel yj, we find. Yeah. Okay. Now, as I mentioned before, we would like to find the adjustment of wji. Yeah. So that is the adjustment for the connection weight in between the input and hidden node. Yeah. So we just deal with this term. Yeah. The most difficult term, and then that is dj, parcel j, parcel yj. Now we are going to do a little bit more. That is, we are going to find out what these two terms they are, and then I just put the result right here. This is the parcel J, parcel Yj, and then we are going to look into the details about how do we find out these two terms. Now, we consider the same system, the same neural network topology, and then we are going to consider a little bit more details about the note right here, because when you talk about this Yj and net j, that means we are going to talk about this Yj and this let j. So let j, that is about x1 times wj1 plus x2 times wj2 and so on. So this is the let j, yeah? So this is let j, the weighted sum of x and w plus the contribution given by the bias. So partial let j, partial wj, this is a partial derivative, and then all other connection weight and x, they are considered to be a constant. So when you do the derivative, and then this one will give you xi, yeah? So this is partial let j, partial wji, and then now we are going to consider another term shown in the previous slide, that is partial yj and net j with respect to net j. So this is yj, and then this is let j. So yj, that is function of let j. So partial yj with respect to let j, that is f prime right here. As mentioned before, f is the activation function. We are going to choose they have to be differentiable, yeah? Okay. Note that this f and this f could be different. So that means when we are talking about the hidden layer, the activation of hidden layer function, and then we have to apply that function when we calculate partial y, partial let j. Now, in the previous 3 slides, our objective, that is to find change of j with respect to the connection weight ji. We are going to find that term by term, yeah? So we break it down into these 3 terms. Now we have this result, and then in the previous slide, we already find out that partial y, partial let j, that is the derivative of f. And then the next term, partial let j, partial wji, that is xi. So when we put everything together, that is partial j, partial wji, that is these 3 terms, multiply them together, that is this term. Okay. Now once you find out partial j, partial wji, and then we can find the adjustment, yeah, the increment of delta wji, that is minus learning weight times this term. Okay. Now I'm going to present you the overall idea again, just to recall what we have done. Yeah. So initially, we are going to initialize the network, find out the training error according to the training data set, and then we are going to find the adjustment, because that is we find out partial j, partial w. Again, this w, that is the collection of all this wji and wkj, and in the previous slide we already know that how to calculate delta wkj, that is the adjustment for this connection weight, and then we also have delta wji, that is the correction or the adjustment for this wji in between input layer and hidden layer. So we are going to apply this update rule at this point to update w, and then we repeat this process, and then this training error will be reduced. Yeah. Okay. So this is the overall picture about the backpropagation algorithm. Now we are going to look at the pseudocode, how actually we are going to train the neural network using the training data set. For example, this is a 3 input 2 output neural network, x1 2 3. These each column, that is an input sampled. For each sample, we expect that the target output that would be given in this T1 and T2. So minus 0.2, minus 7.1, 4.7, and then we expect that the output to be 1 and minus 1. Yeah, if we present this sample into this neural network, and then similarly, when we enter the second pattern into this neural network, we expect that the output would be 0.2 minus 0.5. However, the actual output, that is not the same as this one. So we are going to use this stochastic backward propagation algorithm to adjust the connection weight. This one, take a look at this one. This is the stochastic backward propagation. That is, we are going to reduce the training error sample by sample. Yeah. So this is the first line. We are going to initialize the level topology, that is to determine number of input, number of hidden node, as well as the number of output, as well as to initialize the connection weight in this neural network, as well as the stopping criteria theta, that is a positive value. Yeah, so theta greater than 0, and then the learning weight, that is greater than 0 as well, and the counter m, that is 0. In this do until loop, and then because m, that is 0, that means 0 plus 1 in the first, when we first enter this loop, m become 1. It means that that is the first iteration. In the first iteration, we are going to randomly choose one of the samples right here. So you can see that we have a lot of samples right here. Maybe we just choose this one in the iteration 1. So now x upper script superscript 1, that is this pattern. Okay, so this x superscript 1. Yeah, so because it could be different patterns, because this is a randomly chosen pattern, but anyway, we assume that we choose this one. According to this pattern, we are going to compute delta j, delta k, and delta j according to what we have. Yeah, according to the result, what we have presented in the previous slide. And then now, once we define the learning weight eta, and then this term is well known, and then this term is well known, add it into the current value of w, and then we find out the updated w in both layers. What I mean both layers, that is the connection weight in between input and hidden node, as well as the connection weight in between hidden and output node. Yeah. Now note that when we do this update, delta j and delta k are calculated according to the old value of wji and wkj. The meaning of the old value, that is, we are going to use the current value of w. That is, now if you look at this line, we already update wkj. So when we calculate this delta j, it will cause a little bit confusion if we are going to use the new value of wkj. But when we calculate this delta j, we are not going to use this new value of wkj. We use the old value, that is the value before the update in this iteration. Yeah. So these two lines, we just update the value, and then we are going to check the difference between the j value, the training error, at this iteration and the j value one iteration before. Yeah, so we are going to take the absolute value, so theta, that is, must be positive. That means we are going to check how small the difference between the current and the previous iteration, I mean the training error. If it is small enough, we are going to stop. So if it is not small enough, we go back to the top, increase the value of m, and randomly pick another sample, and we repeat this process to update wkj and wji. Yeah, so this is the stochastic backpropagation. Yeah. Now take a look, and another approach, because as I mentioned, that stochastic backpropagation, that means each time we just pick one sample to minimize J. Now we are going to do the batch backpropagation. It means that we are going to use all the samples in the training data set. So when we consider the first sample, we can compute J1. When we consider the second sample, we can compute the training error J2 due to the second sample, and then extend that to the last sample. So the total training error, that would be the sum of J1, J2, Jn. Yeah. So now I'm going to present you the batch mode backpropagation pseudocode. Now take a look at this one. We are going to have this sample. We are going to have this training data set. This is the target value, and then the actual output we can measure it right here when we present the sample into this neural network. So the backpropagation, the batch mode, we start with the same line, that is to initialize the network topology, that is D and H as well as C, and then to initialize the connection weight of this neural network, the stopping criteria, learning weight, as well as the counter. Now the counter, that is R, that is initial value, that is 0. So we call this is the increment epoch. So when we first enter this do loop, R becomes 1. It indicates that that is the first epoch. In each epoch, we are going to go through this process for n time. Yeah, so n, that is the number of samples right here. So if we are going to have 100 samples, and then so we are going to repeat this process for 100 times. Yeah, take a look at what we are going to do in this loop. We are going to set up a local counter m, that is 0, and then so we are going to set up another two variables, delta wji and delta kj, that is 0. Yeah, so that means when we first enter this line, these two values will be 0, and then the counter will become 1 according to this increment. Now we are going to select the mth pattern, because when we first enter that in this line m, that is 1, it means that we are going to choose the first pattern, and then with the first target value. Now compare with the previous stochastic backpropagation algorithm. The sample is chosen randomly, but now it is not. We are going to consider one by one, starting from the first samples. According to the first sample, we are going to compute this value as well as delta k and delta j. We are going to add it to these two variables. Remember that in the beginning, these two values, they are 0. So now we are going to add this to 0, and then this delta kj, the new value will be these two values. Yeah. Okay. Go back to the top. M become 2. It means that we are going to choose the second sample with the second target value. We can compute a new value of delta k and delta j according to this new sample. Remember that in the first value of m, this is delta w is contributed by the first sample. Now we are going to add the contribution given by the second sample. Yeah, and then we repeat this process. We move on to the third, and then so we are going to add the delta k and delta j, the contribution made by the third sample, and then put it into this buffer delta w. After we go through all these samples right here, that means we already find out the contribution delta k and delta j made by all this sample, and then so we are going to add these two values into wk, j and wji, and then update the new value, update the connection weight of wkj and wji. Again, we are going to use I think that we are going, yeah, okay, so right here we are going to update these two w using these two deltas, and then now we are going to do the same thing. That is, now we are going to calculate the J value, the training error due to the whole data set right here, according to the previous slide equation, and then the J value in the previous iteration or the previous epoch. If the change that is less than theta, and then we are going to stop. It means that the performance is good enough, so we are going to stop. Yeah. Okay. If not, we repeat this process in the second epoch. We are going to update the W as well. Okay. Now I'm going to talk a little bit about the learning curve. That is, usually I just mentioned about the training data set, but actually we can divide the raw data set or the overall data set into the training, validation, as well as the test set. The training data set, that is to train the W, the validation set, that is just to give you some indication when to stop the training if you're not going to use this stopping criteria. Yeah. For example, during the training, and then so this is the J value. Yeah, this is the J value using the training data set. But actually we are going to normalize that divided by the number of samples. Yeah, so because we use the gradient descent, the training error, the value of J should be decreasing. Yeah, simultaneously we are going to fit in the validation set into the same J, so that maybe the curve is something like this, up and down. Yeah, and then the same applies to the test set. We fit in the test data set into the same J, and then so it will have different behavior. Yeah, but the reason why it goes up and down, it is mainly because these two validation set as well as the test data set, they are not used for training. The adjustment of W, that is not to reduce the value of J due to the validation set or the test data set. The reduction of J mainly due to the training data set. Yeah. But the reason why we are going to do the validation set, it is because the validation set, it just gives you how good the training is going to be with some unseen data. Yeah. So one of the stopping criterion, that would be when the validation set, the curve, which the smallest value, or it is going to start to increase, and then we are going to stop. Yeah. So for example, right here, we are going to stop at the epoch 5. Yeah.